Hello. So, welcome to the live session. I'm Virmala Roy. I'm a research scholar in IIT Kharagpur Mechanical Engineering Department. So, I'm the uh, TA for the course of Introduction to Fluid Mechanics. So, today we'll be looking at assignment 2. Uh, we'll be studying based on the assignment 2. So, yes, let's dive into the first question straight away. This here it is given the viscosity of a fluid is to be measured by a viscometer. So what is a viscometer? Viscometer is a device for measuring the viscosity of a fluid. So the arrangement is represented in this figure. So the fluid is present in this dark orange region, and there is a stationary cylinder here. This is not rotating. This is stationary, and this is the shaft. This yellow color cylinder. This is the shaft, which is rotating at an RPM. The RPM is also given. So this device, as it is already stated here, uh, is to be used for measuring the viscosity of the fluid inside this device. So why are we rotating this shaft? So basically, we will find out to reach this RPM how much torque is required. So that torque should be same as the resistance provided by this fluid due to its viscosity, and from there we will calculate its viscosity. So, so yeah, the question here the in the question some assumptions are like uh, given. So the fluid layer thickness L, which is basically the gap between the two cylinders. So this is outer cylinder and the inner cylinder. So the gap between this is represented by small m, and uh, this gap is taken to be very small. And uh, also it is to be like it is understood that the ends of the shaft, the whatever the friction or the resistance is there due to the end effects, those are to be neglected, and only resistance that the shaft is getting is to be assumed that it is provided by the fluid's viscosity, with the like the viscous stresses of the fluid acting on the surface of the shaft. So here, since it is mentioned that this gap, this gap is very small compared to this R. So this L is small compared to the R. So we can also like see from here the this is the outer diameter of the inner cylinder is 12 centimeters. So this is 6 centimeter, and the gap between the cylinders is 0.15 centimeter. So this is basically the radius is 40 times larger compared to this gap. So if this length scale difference is there, we can consider this gap as a narrow gap, and uh, the, by considering this gap as narrow gap, we will assume that the velocity variation that is taking place of this fluid is linear. So we will draw like let's draw one section of this. So this is like a zoomed in section for the cylinder. So this is like a zoomed in section, and so this is the outer cylinder, and this is the inner cylinder. So the outer cylinder is stationary. So if we have to draw the velocity profile of the fluid between this inner and outer cylinders, so this is stationary. So here the velocity, let's represented using V. This is 0 because of the no slip condition. So fluid stationary to the wall will not move with respect to the wall. So that's why the inner cylinder, what will be the velocity here? This will be the velocity in which the inner cylinder surface is moving. So since there is no slip condition tells us, like we will apply no slip here. So it says that the relative velocity between the wall and the fluid is 0. That means wall is the fluid is adjacent to the wall is basically stuck to the wall. So when the wall is moving, the fluid adjacent to it will also move and in the same velocity. So let's suppose this velocity is capital V. So this is moving at a capital V. And since this gap is narrow, what we will assume is this is linear. The velocity variation between. So we have got the velocity at this wall and we have got the velocity at this wall, but we still have not got velocity at all these points. So what we will do, we will make an assumption that this variation is linear. So since the gap is narrow, whatever the higher order variations will be there, those are negligible. And later in the course, we will also see that if there is no no variation with time uh, of the geometry and the velocities, and there is also no applied body force like pressure or electric field. It also always comes out to be linear profile. So this is called uh, Couette flow. Couette flow problem that we will encounter later in this course as well. So this velocity is v, and here the velocity is 0. So like if I define a coordinate here, let's say this is y equal to 0 and above this is the y-axis. So how is it varying with y? So this v, which is a function of y, this is at v when y is 0, it is v, and uh, when y is smaller, y is equal to smaller, this is 0. So this is this will be v minus uh, v by. So you can see if I put y is equal to 0 here, this is v, and if I put y is equal to smaller here, this will be 0, and this is linear because only y term is there. There is no y square or any other function of y. Only y term is there and a constant is there. So this is a linear equation. So maybe I can also write it like this. L. Okay. Now, what we actually have to find, we have to find the force applied on this inner wall, right? We have to find out the force applied on the inner wall due to the viscous effects. So, where is viscosity coming from? So, viscosity is basically which is the property of the fluid which is not um, letting it move, which is providing a friction. Like since the momentum adjacent to the wall is 0, there is no need for the momentum of the fluid above the wall to also like be close to the relative velocity. So say, since there is the variation of this is gradual. So what is actually happening? The the fluid adjacent to the wall is stuck to the wall. Fluid adjacent to that is trying to follow the layer beneath, and over that it is again trying to follow the fluid adjacent to it. So the relative velocity it tries to minimize the relative velocity, and it like tries to basically slow down the momentum exchange. So for that there will be a force which this fluid applies on this inner wall. So this inner wall is the wall of the shaft. So this there will be a traction vector at this point. There will be a traction vector which is basically the surface force that the fluid applies on the wall. So we already uh, We have seen in the lectures that this term, the fraction, the shear stress term, which will be basically applied. So what we are doing, we are neglecting any normal component that we are not considering, because that will not like slow down the rotation of the cylinder. So if there will be like no torque on the cylinder due to that, because this is a circular cylinder. This is a circular cylinder, and if there is any like normal force also, then the it is not affecting the uh, rotation. However, we are very much uh, like uh, we need to very much account for the tangential component of the forces applied there. So the tangential stress. So I'm currently like focused on stress, which is the force per unit area here. So this stress component due to viscous effects. So at the wall. So let's say this is tau wall represented by tau wall. This is given by mu del u del y, del v del y. Since we have taken v here, so del v del. So uh, so what is this? This is basically the stress applied on the fluid. So we will calculate this. So here del v del y. What is del v del y? This is if I like differentiate this just with respect to y, we will keep everything else constant. So there is no other variable in fact. So this comes out to be simply v pi minus v pi. So there is a minus sign here, and this is v. So this is the tau wall. So this component is applied by the fluid on the wall. Now, uh, so this component is applied by the wall on the fluid. So what will be the by the Newton's third law, the force applied on the this inner wall will actually be the reverse of it. So it will that will be stress will be on a tau wall. This is now what is the total torque that we have to find out, right? Torque is basically force, whatever the force, total force is there, force into r, the radius of the inner circle. So, like, let's refer to this figure once again. So, what we have done so far is calculated the fraction vector at this point. Now, we have to integrate it over the whole thing. So, we have the stress, and we have to integrate over the whole area to find out the total force. So, this will be the force. Now, then we have to find out the torque, which will be force by r, force into r, because this is r distance away from the center of rotation. So yeah, so this is r, and this is basically forces, as we saw. This is integration mu v by l is there, and this is basically dA, which is the area. So these are all constants. So this will come out. So this is mu. What is v? V is the velocity of the inner cylinder at this point. So what that will be? That will be simply omega into r, where omega is the this r rotation, the angular velocity. So I can replace this using omega into r. So this is the constant. This into area, because this is integration dl, so that will be area. So what is the area? Area of the cylinder, surface area of the cylinder. This is basically 2 pi r capital L. Capital L, I am representing the length of the cylinder. So don't confuse with the capital L and the small l. Small l was the uh, gap between the outer and the inner cylinder. So we found out the torque with that. So we'll go to the next. Yeah. So we have found out the torque. Torque is 2 pi 2 pi r cube omega L by rect. Uh, oh, sorry. Yeah, obviously omega will be as well. So mu will be about small L. Yeah. So from here we can easily find out what is our viscosity. So we will uh, uh, put the viscosity on one side. These most of these are just geometric parameters. We can measure them, and since we are operating the shaft, we will know the torque. We will know uh, the omega, the RPM. So we can set the RPM of this and like calculate the electrical power that the shaft is consuming. And from there, like we can calculate the mechanical work done with this with this torque and omega. We can find out like the torque. Given the power and the RPM, we can find out the so this can act as a device for measuring viscosity. So now we have to do this, find the viscosity, right? So we have to find the viscosity. All these data are given. L is given, so this is L, this is L, this is outer diameter, so this is 2R. 2R is given, and gap between this is small L is given. This is omega. So units you have to change because this is in RPM. You will require it in radians per second. So that you have to change. The torque is also given. So TL these are given. If you put it in this, you will find out the answer. So exactly that's only what is given in the solution. So how to find this B is given and this matches with the expression we just derived. If there is any problem, you can like ask me that in the next question. So, yeah, so this is the answer. So let's go to the next question. So the next question is consider two identical glass balls dropped into two identical containers, one filled with water, one with mustard. Which ball will reach the bottom of the container first? So the problem is very simple. You have a container, you have a ball, you are dropping the ball. Now, first of all, why? Let's consider the first option. Both balls will reach the bottom at the same time. Like we all know, what is making the ball come down is the gravity. So if there were no fluid, what will happen? Wherever you hold two balls, irrespective of the mass of the ball. So even if they were not identical, we know like if we neglect any fluid friction, the balls will hit at the same time because like that is a property of how gravitational acceleration works. So if the gravitational mass and the inertial mass they will cancel out and they will both the balls will hit the same time. Now it is also said here it is two identical balls and so there is no mass difference as well. But still, will the first option be correct? Will not be because there is fluid friction involved. One is falling inside water and another is falling inside mustard. So there must be some property of these fluids which is influencing their fall time. What is it? That is viscosity. That is the friction of the that the fluid is imparting on the two balls. So first option is definitely not true. Both balls will not hit the bottom at the same time if they are on different fluids with different viscosities. Water and mustard oil have very different viscosities, and that is what we actually need to really solve this question. So let's come to option D because this is the information that we actually need to really answer this question. Is this true? Water has larger viscosity than mustard oil. It is not. So, like water's viscosity is about 10 to the minus 3 parts per second. And a mustard oil's viscosity is generally two orders higher than that. It will be in the range of 10 to the minus 1. Yeah, like most oils have very large viscosities compared to water. And their like viscosity is also vary with temperature a lot, but still the values are much larger than water. So this is false. Now, if this statement is false, now you know the answer. Why? Whichever fluid has a larger viscosity will uh, slow down the balls, uh, even uh, will slow down the balls more. So the fluid where the viscosity is less, there the ball will drop first. So if we read the options, yeah, this B is the correct answer. Ball dropped in water will reach the container, end of the container first, because water has less viscosity compared to mustard. So this is a very easy, simple question. So here it is explained. So here it is written the typical values of viscosity is approximately 800 times greater than water. So at room temperature. So if it is so high, obviously it will be noticeable. The fall will be noticeably slower. The ball will have very low viscosity. So what are the forces acting here? So one force that is acting here is the gravity force, and the other force acting here is the viscous force that we have discussed. Okay, so this gravity force is mg, and what is the same? M is the mass of this ball, and what is the viscous force? Viscous force is actually given by Stokes law. So 6 pi mu r v, where v is like the velocity, and this is the dynamic viscosity, and r is the radius of this ball. So means at when the ball gains a steady velocity, then this equation will be followed. But there is another force also acting, and the um, word identical is very necessary in this case because of that force. Uh, like obviously because of gravity as well, because gravity balances these viscous forces. So gravity is this mass is also very important here. Another shape wise also there is another force which is very important, that is the buoyancy force. So what is buoyancy force? Buoyancy force will also act upwards. That is, this will be mass of the fluid displaced by this volume. So this inside this volume, if this whole volume was covered with the fluid that this wall is in, so whatever the volume is inside, this this is the this is the force acting on this. So if there is no acceleration after some time, like if the ball gains a steady velocity, even if it doesn't, then also we can calculate actually. So let's say capital M is the mass of this ball. So this will be something like this. Ma will be summation of all forces. So let's say this is the positive direction of the acceleration, downwards direction. So then, what is the force acting downwards? This is this. If there were no fluid, then this is the basically this is the equation. So n will cancel out. The acceleration will be equal to acceleration due to gravity g. But since there are fluids as well, there will be two terms here. One is this. So this is, let's say, the volume of this ball is v. So this will be rho into v, right? V, where rho is the density of the fluid, minus this viscous term. So viscous term, we can write F viscous. This can be calculated. So there will be a viscous force, this and that. So when acceleration is zero, basically this gravity is balanced by this viscous and the buoyancy forces, and we can find out a terminal velocity from this equation by equating this forces. Okay, let's move to the next question. So here also there is a graphical representation of the problem. Mm, and what we can see is that there's between these two walls, the fluid is filled in, and there is also a plate here. So this plate is at a particular position inside this between this wall. So this is 1 meter towards the bottom of from the top. So, and this plate is being pulled uh, by a force F. Hmm, force F, and what is actually maintained is this velocity, 1 meter per second. And this bottom wall is also moving in this direction with a velocity of 0.3 meter per second. So what we have to do here, we have to find the location in which oil velocity is zero. So this fluid is oil, and there will be a velocity zero here because you see, if you consider just this part of the plate is moving with 1 meter per second. So whatever fluid adjacent to the plate will also move towards that direction at 1 meter per second. And similarly, if we apply no slip condition in this bottom wall, the bottom wall is moving uh, in this direction at 0.3 meter per second. So that is the fluid adjacent to the bottom wall will also move towards that direction. Since they are moving in the opposite direction, there must be a point where the velocity changes direction in the fluid, and that we have to find out. So that we can easily find out because we what we know is that this fluid profile, this profile is linear. So that assumption we will make because like we as we previously described, there is no like external body forces like pressure and all, and also this can be taken as a very narrow gap. So how it can be taken as a narrow gap? One length scale is given here. So yeah, this is 20 centimeter flat plate. So this is like the length of along this x direction. Hmm. So this is 20 centimeter, and let's say this gap is h2. Here it is given. So h2 is uh, sorry, h2 is in millimeters, right? So it is 2.6 millimeter. So this is basically about almost like two orders of magnitude higher. So we can consider this gap as a very narrow gap. The fluid variation will be linear. So we have basically a very linear kind of equation. So we have to find out when this is becoming zero. So let's say the velocity is given y. So uh, this is linear. So I will just give a linear equation a y plus. Let's say fluid profile is this. Now what I know? I know when y is 0, uh, u is minus zero point 0.3. I have to give this minus to maintain the direction. So I got this is equal to y is 0. So this is 0. So I have got the value of v. And also I know when y is equal to, let's say, yeah, let me do like keep the unit as millimeter only. So 2.6 millimeter. Then I know u is equal to 1 meters per second. So this was also meters per second. This is meters per second. So from here I can uh, find out a. So this a will be nothing but if we just calculate, we will find this. This is 1 by 2.6. This is meter 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 by millimeter. So second. So you can cancel this, and there will be a 10 to the 3 here. That you can do. So that will bring a 10 to the minus 3 at the top. 10 to the 3 at the top. Sorry, 10 to the plus 3 at the top. So we got A, we got B. Now what we have to do is basically put y is equal to 0. So u is equal to 0. Sorry, u is equal to 0. Let me like do it here only. Yeah. Do it. So 0 is equal to ay plus b. So the answer will be okay. Did I? Yeah. So this will not be one, right? Okay. This will actually be 1.3. Okay. Thanks. So this is 1.3. Yeah. 1.3. So because this b value is there, right? B value have to take y will be equal to minus b by a, and I can calculate this. So this is let's do it. This is simple enough. So above there is zero point 0.3 from this b, and there is also 2 here, right? Uh, so 2 is at the top. Yeah, 2 is at the top, and there's 10 to the power 3 at the bottom. So 10 to the power 3 at the bottom. This will be in meter. So 10 to the power 3 at the bottom will make this millimeter, and this zero point 0.3 into 2 will make it 1.6. So this should be the correct answer. Yeah. So they have basically done the same thing. Uh, yeah. So whatever you way you can do it, you can use the similarity of two triangles also. Just take the ratios and from there on you will get the answer. So how will this method work? Similarity of two triangles. So basically our profile looks like this. So we will just do it geometrically. So we know this is one and this is zero point 0.3, right? This towards this side 0.3. And we also note that this whole distance is 2.6, right? So, so if this is one, hmm, let's say I want to find out this distance, right? So let this be x. So x by zero point 0.3, hmm, this will be equal to this 2.6 minus x. This will be this guy, right? So this can be solved, and this you will reach the same solution. Let's go to the next question. So this refers to the back to the previous question. So now what we have to do is find the f, find the force f. So if we recall, this was being pulled by a force f. So we have to find this out, and here we will require this area because we can find out like we did in the previous problem as well. In the first problem where there was a viscometer, so we will find out the stress, shear stress acting on the surface. Then we will integrate it over the whole area. So let's do that. So here also, uh, so we already know the drill. So the area will be there, and here also since the shear stress is not varying, so the integral in the integral the shear stress will come out, and there will be integral dA. Hmm. Let's refer to this problem for better understanding. Here only. Uh, yeah. So here I have written. So F is integration tau dA. Now tau is if tau is constant, it will be integration dA. So that will be simply the area. So, so in this question, here also we will have area into the shear stress of the wall. So that will be del U del Y. What is this? This is basically our A. What we have. Uh, don't confuse it with this. So in this equation we have done ay plus b. So this a is the slope, right? This is the slope in a linear equation. This will be the slope. We'll put the values there. So this is 20 centimeter into 20 centimeter. So viscosity of the oil is given here. This is 0.027 Pascal second. So I put 0.027 Pascal second into this coefficient we had calculated as this is basically 1000 divided by 2, which is 500, right? So this is 500 per second inverse. So I have written down this units so that we don't get confused because there are like centimeters, then there is meter somewhere. You can also convert everything into a standard units like meter and second and kg. That also will save all this. And we will do that. We will like simply take this as point two. So meter square and Pascal will be become Newton, and this second inverse and this second cancel out. So this will basically be 0.04 into 0.027 500. So that will give me 20 into 0.27, 0.027. This is, yeah, 20.27. Let's see the calculation here. Yeah, 0.54. So have they not asked? Oh, okay. So we have to do the same exercise for the above side as well. Yeah. So this is this side. In the above side as well, the same exercise needs to be done. So here we get our force as 0.54 Newton. Okay. Uh, for the this is, let's say, F1. So towards the top surface, it will be F2. That is same area into mu. Del u del y will be different. So let's calculate the slope here as well. So this is our velocity profile. So here velocity we have been given as 1, and the height is also 1 mm. So this slope will be simply 1 meter per second divided by 1 mm. Right. This is basically del u del y. Since this is constant, we can write it as the change in the velocity, which is basically 1 meter per second, because at the top wall the velocity is 0, and also and divided by the gap height, that is 1 millimeter. So this is basically 10 to the power 3. Right. This is 10 to the power 3. 10 to the power 3 second inverse. So uh, instead of 500 here, we will have 1000. No other difference, right? No other difference. So, so it will be exactly double of this, which is 1.0. We will add them up, and so the total force that this plate is subjected to for moving it in the constant velocity of 1 meter per second is basically F1 plus F2, which is 1.62. This option C is our answer. So be careful with the units. This is not kilometer. So the same exercise has been done here. All right. So the next question is, this question we have also done in the, if you recall, we will have done in the week one, where we solved the preliminary mathematics of fluid mechanics. So there, the first question I think was to find out dimension of something. So yeah, this is very similar question. So let's try to do it with the relations we have learned recently, which is like we have learned to equate the stress at the wall as mu del u del y. Now the dimensions of both sides of the equality must be same, and we know this is stress. So this is, let's do it with units only. That will be easier for us. So this is in Pascal. This is Newton per meter square. And mu, this unit of viscosity we have to find out. So what is this? This is dynamic or kinematic? This is the dynamic viscosity. So dynamic viscosity is mu. Kinematic viscosity is basically divided by rho. So why is this the like easier way to remember this is, when we are talking about kinematics, we are not talking about we generally do not uh, talk about the forces involved. So we are not concerned with the inertia or anything which like what does inertia do? Inertia basically, if we apply a certain amount of force, the inertia is the resistance for it to change its momentum, hmm, due to that particular force. Now, if I am dividing by like the inertia, the force I am dividing by the inertia, this is basically the tendency of how much the acceleration changes. So now we do not have to like we have kind of taken a ratio. So this viscosity is basically the same thing. Viscosity is a friction between the fluid molecules. So this are a type of like it represents a force. And when we are dividing by rho represents the inertia here because this is the density, how dense the fluid is, how inertially dense the fluid is. So if I divide it by the density, so it is like I am dividing a force term by a density term. So that will only give up me the kinematic number. It will try to give me the scale of the acceleration of a fluid. Of a particle. So this is a very like vague way of understanding it, but we can understand why this is called kinematic, why dynamic, and why mu is called uh, dynamic, dynamic viscosity. So uh, this is represented with mu. This is another Greek letter. Alright. So, mm, yeah. So this unit we have to find out. Here above it, this is velocity, so this is meter per second, and this is a length, so this is meter. So here we can find that the unit is Pascal. We know this. We represent viscosity all the time. So we know this. So we can break this Pascal because this is not the very fundamental. This is not a unit of a fundamental quantity. So we'll break this down into kg per meter per second square. So kg meter per second square is force divided by area is meter square. So this is kg per meter per second square, and this second square. So this is basically the unit is kg per meter per second. So what corresponds in the dimension? So this is the first option, right? First option, yeah. So only one option is coming out to be correct. M L minus one, T minus one. So let's check with our kinematic viscosity as well. Kinematic viscosity, this is basically, this will be mu by rho, the density. So this we have, let's write it in terms of Newton second. And what is density? Density is kg per meter cube. Hmm. So m minus 3. So we will have here meter square. So we can see option 1 is correct. Both of these are correct. So this is the correct. This must be pretty easy for you. So here the same thing has been described. Let's move to the next question. So here have we were like discussing about this tau wall is equal to mu del u del y. So here what we had done, we had assumed this y to be constant. So this tau is basically my shear stress. So here in the graph you can see this is the shear stress axis. And what is del u del y? Del u del y is how much what is the rate of shear? So a fluid element, how much like with what rate it is deformed, that will be given by del u del y. Because like you can intuitively understand, like if you take a fluid element like this, if you like consider how much the fluid is changing, the like the velocity at the top portion and the bottom portion, how much they are different, that will give you an idea how fast this fluid element is deforming. So that is rate of change, rate of shear. So this is basically representation of del u del y, and this is representation of my tau wall or tau. So here Till now, we have only done constant mu. Constant mu means like the slope is constant between these two. What we call it, we have called it Newtonian. So this 2, which is a straight line, this corresponds to a Newtonian fluid because here the slope is same. This is a straight line, the slope is same. So mu is constant. So we have till now studied only Newtonian fluid. So we have to match here. I think, yeah, we have to match these elements with here these curves. So Newtonian fluid we can match with. So let's uh, see what are there options are there. So for all of them, it's two only. Yeah. So all of them have two. So any of these options may still be correct. So let's discuss each one of them. So what is a pseudoplastic fluid? So pseudoplastic fluid. Let's first discuss what is a plastic fluid. So plastic fluids also sometimes known as Bingham plastics. No, so Bingham plastic fluids. So what are these? These are basically like if you provide some amount of stress, it first behaves like a solid. So, uh, so the shear, uh, it is not proportional to the rate of shear, but like the amount of shear only. So the rate of shear is zero. As soon as like you withdraw the stress, it won't keep on flowing. It will retain its original position, or like it will retain some like some configuration, but it won't keep on deforming like a fluid. So, but once you provide a certain amount of stress, after a certain threshold of stress, if you provide more stress, it will start to have a rate of shear. That means it will start to flow like a fluid. Hmm. So only after a certain threshold of shear stress, it becomes a fluid. So those are called plastic fluids, Bingham plastic fluids. So what corresponds, which curve corresponds to that is this curve 5. Why? Because here, after a certain amount, here it is mentioned as yield stress. After a certain amount of stress, we provide more stress, then only the rate of shear uh, takes place. There is a rate of shear. So this is called a plastic. So this R is represented by 5. So what is pseudoplastic fluid? So pseudoplastics are basically like you will feel while giving them providing them shear stresses that they are becoming easier to move as you provide more and more stress. So what happens is basically this mu value, the viscosity value, will decrease as you are providing with more stress. So this viscosity is basically stress, the slope of this curve, right? So the slope of this curve. So here it is unlike the plastic fluid, pseudoplastic fluids from the beginning itself they display some rate of shear. So this flows unlike plastic fluid. So but the viscosity at first is higher, and as soon as the as the shear stress keeps on increasing, this viscosity starts getting lower and lower. So the slope of this curve becomes low. So this is called a pseudoplastic fluid, or this is also known as a shear thinning fluid. So this is as if the fluid is becoming thinner. It is becoming less viscous as I provide more and more stress. So which one corresponds to that? This fourth. So this Q is 4. What is dilatant fluid? Dilatant fluid is basically the opposite of pseudoplastic. Here, as you provide more and more stress, it becomes less. It becomes more and more difficult to make the fluid flow. So it as if the viscosity is increasing as I am increasing my stress. So here the graph will be exactly opposite. So the slope will continuously keep on increasing. So this is my dilatant fluid. Okay. This, yeah. So my answer P2, Q4, R5, and S3. P2, Q4 R5 SC. So I think, yeah, this one, right? Correct answer is C. So here they have also provided um, this nice curve which describes basically all the fluid regions, the Newtonian and the other types of fluids which are known as non-Newtonian, basically because their viscosity varies with the shear stress given. So we can have dilatant uh, fluids which thickens, like becomes more viscous as you apply more stress. You can have pseudoplastics which becomes less viscous as you apply more stress. You also have Binghams. Binghams may be plastics. So after a certain amount of time, it's showing its fluidity, or it can be also ideal Binghams. So ideal Binghams are basically like after a certain amount of stress, they behave like a Newtonian fluid. So after a certain threshold stress, this curve has suddenly become, you can see, linear. So this uh, after threshold stress, it is becoming a Newtonian. So yes, and along the axis we have the ideal solids which never flows. There is never a rate of shear associated with the shear stress, and also there is an ideal fluid where basically this is basically when viscosity is zero, or like so super fluid, ideal fluid, no viscosity. So let's go to the next question. Next question is just basically a assertion reasoning. So here assertion is there that the blood is a Newtonian fluid, and reasoning is given as the rate of strain varies non-linearly with shear stress per blood. So let's like is blood is Newtonian? It's not Newtonian. So both of these statements A and R are contradicting. Why? If the rate of strain varies non-linearly with stress, this is basically definition of a non-Newtonian fluid. So and this B is therefore true. This R is the second statement is therefore true. This is true. This is false. So let's see. Yeah, both these first two options are wrong because individually the first one is wrong. So A is false, R is false. This will be the correct answer. So yeah, so your blood is shear thinning fluid. That means that it will fall in the pseudoplastic category. So this is shear thinning. Blood rheology is the more complex because of the various components that blood has. That is a like separate topic. But like if we want to analyze blood flow, it is generally taken as a shear thinning fluid. Okay. Uh, yeah. So I think this is from this next. This is the last question. I guess. So you have to examine these two statements carefully and select answers uh, on based on these two statements. Well, let's see what are the statements. So statement is at standard temperature, kinematic viscosity of air is greater than that of water, and statement two is dynamic viscosity of air is lower than that of water at the same temperature. So for this we have to know the viscosity of air, water, and the density of air and water. So obviously you from intuition only you can understand whose density will be greater, water. In fact, like a lot greater. So water's density is you can take it as 1,000, around 1,000 kg per meter cube. It varies depends on the temperature, and air also varies greatly on temperature, but it is like on the order of like 1.2 kg per meter. So this is almost like 1,000 times. Air is very light compared to water. Water is heavy. What about viscosity? Viscosity also, like if I take dynamic viscosity, yeah, so the dynamic viscosity of water is 10 to the power minus 3 Pascal. Where if air is definitely less viscous, the air resistance and the drag due to water, it is very different. Like water gives a lot more resistance compared to air. Like you can make do a free fall. You can dive inside water. The water will slow you down. So due to gravity, you will not like crash and break your bones. But if you just dive in air, like it is like falling from a building. You will break your bones. So, but with water will slow you down because of its higher viscosity. So, it's 10 to the power 3, and air is approximately like 10 to the power minus 5. Like it's in this order. Water is about 100 times more viscous than air. Okay. So let's see. What about kinematic viscosity? Kinematic viscosity is basically the ratio. Hmm. So ratio of the water's 10 to the power minus 3 divided by 10 to the power 3. So this is 10 to the power minus 6. And what about air? Air is 1.2. Uh, this is 10 to the power minus 5 divided by 1.2. Hmm. So this is basic. So here you can see that this is close, but actually, like the value that you will get for lesser for the air. So this is like if I consider this, so this is almost 10 to the minus 5. Hmm. So, if I take kinematic viscosity, the air viscosity will be greater than the water. So this is true. Hmm. If I take the ratio. So basically, what does it mean? Uh, even though the resistance of water is greater and the density of water is greater, if I like divide the inertia by it, the tendency of changing the acceleration due to like same force by inertia is greater in terms of air. So it can like change its acceleration very more quickly. So uh, and what about this? Dynamic viscosity of air is lower than that of water. So this is definitely true. Air is like in our when we talk about viscosity, we generally talk about dynamic viscosity. Air is definitely less viscous than water. So both are true. So we will have the correct answer is A. So both are true. Here also like the values are given. So this is like given 50 times. So we can calculate it, and what we have found, we have calculated it. We have what we have found for air. This is approximately 10 to the minus 5, the kinematic viscosity, and for water, this is approximately 10 to the minus 6. Okay. So if you have any doubt regarding like this assignment, any previous assignments, or topics related to this assignments, please like feel free to join the next live session, which will be on Tuesday at next Tuesday at 7 p.m. and we can like feel free to discuss them.